Before 1998, medical researchers faced a massive blind spot. We knew zero gravity caused changes to the human body, but we lacked the data to understand what happens when humans live in space for months or years at a time. To get that data, researchers needed a dedicated laboratory orbiting the Earth. Up to that point, missions were mostly brief trips. There was no permanent off-world facility where long-term biological studies could be conducted continuously. This diagram of orbital velocity outlines the core problem. To keep a laboratory from falling back into the atmosphere, it has to constantly travel at 28,000 kilometers per hour. Surviving those violent physics meant engineering a structure so massive and developing technology so advanced that no single nation had the budget or the industrial capacity to pull it off alone. The solution to that engineering bottleneck was geopolitical. 16 different countries agreed to pool their budgets, their engineers, and their specialized technologies into a single cooperative effort. We can see the scale of what they agreed to build on this comparison chart. The finalized design called for an orbital facility weighing about 420,000 kilograms, roughly the equivalent of a small fleet of commercial airliners. In terms of sheer volume, the sprawling array of living modules and solar panels required enough space to cover the entire length of a football field. The math of keeping it in orbit was difficult, but the real barrier was terrestrial logistics. They had to coordinate components built in factories across 16 nations, ensuring everything fit together perfectly in a total vacuum. That multinational assembly process finally began in 1998, when rockets lifted the very first structural components into the upper atmosphere. Because of its sheer size, the station couldn't be launched all at once. It had to be launched module by module, requiring astronauts to physically bolt these multi-ton pieces together while floating outside the craft. 2 years of this dangerous, high-altitude construction eventually yielded enough pressurized living space. By November 2000, the first crew officially moved inside. That specific month marked a hard transition. What had been a series of blueprints and scattered parts was now a permanent, continuously inhabited outpost orbiting the planet. Moving into that outpost meant adapting to an environment disconnected from regular time. At 28,000 kilometers per hour, the station circles the Earth every 90 minutes. For the crew, the sun rises and sets 16 times a day. There are severe biological threats to living in this state of microgravity, where weightlessness means the human body no longer has to fight against the Earth's pull. Without that constant resistance, astronauts experience rapid, severe bone density loss. To survive, the crew is placed on a strict biological countermeasure protocol. They are required to strap into specialized resistive machines and exercise for 2 hours every single day, just to keep their skeletal structures intact. Keeping the crew fueled requires an entirely separate logistical chain. Because space prohibits standard cooking, the daily diet is strictly managed through rehydrated meals and vacuum-sealed packaged reserves. Those baseline calories have to be reliably replenished. The station relies completely on external supply ships, which are periodically captured by the station's robotic arm, delivering vital cargo and the rare luxury of fresh fruit. The scientific research is the main objective, but simply staying alive to perform it requires an intensely engineered, hour-by-hour battle to maintain basic human biology. Today, all of that construction and maintenance has resulted in a sprawling facility. The International Space Station operates as a fully realized floating laboratory complex. Inside, crews run hundreds of simultaneous experiments that leverage the weightless environment. They stress test new synthetic materials and even navigate the complex botany of growing and harvesting edible plants off-world. The data gathered from these zero-gravity experiments directly translates to industries back on the ground. The research yields refined protein crystals for better medical treatments, advances in closed-loop water purification, and accurate global climate change tracking. By isolating variables in a way that is impossible under Earth's gravity, the station generates measurable, life-saving technological advancements that directly serve populations down below. However, the structural lifespan of the facility is finite. NASA is currently finalizing plans to safely deorbit the station and guide it into a controlled atmospheric burn around the year 2030. Bringing the structure down is the final step in a calculated life cycle. It marks the successful completion of Phase 1 in human space habitation. The decades of medical monitoring and logistical problem-solving we compiled on the ISS have mapped out exactly how the human body degrades in space, and exactly what it takes to prevent it. That data is the foundation for our upcoming extended missions to the Moon and Mars. 16 different nations solved the logistics of assembling a multi-ton habitable structure while moving at thousands of kilometers per hour. By doing so, they engineered the vital groundwork for humanity's next step into deep space.